Hello, my people. All right, so you'll probably hear my dog whining in the background of this because I've banished her to the basement because she's too loud. So I do. My apologies. All right. So yesterday we talked experimental probability. Remember that was, well, that's at the bottom here, so I won't answer that just yet. All right. So today we're talking theoretical probability. Theoretical probability is the number of ways that an event can occur over the total number of equally likely outcomes. And this idea of equally likely, I'm not going to go through the examples and stuff, is just every outcome is fair, okay? So, or is equally likely to happen. So if you take a look at this example right here, this is an equally likely outcome because each of these occupy a fourth or 90-degree angle of that circle. So I could just as easily land on blue, yellow, red, or green. In this one, I have very small yellow, smaller green, about a quarter of it is red, and then about half of it is blue. So those are not equally likely. So if you roll a die, and like the die is weird and it has 2 3s on it instead of a 1, 2, 3, 4, 5, or 6, then obviously like those aren't equally likely. All right, so you have to make sure you're dealing with equally likely events when you deal with theoretical probability. So what's the difference between theoretical and experimental? Well, we talked about this yesterday. Theoretical is what should happen. So in a perfect world, here's the math of it, right? Experimental probability is what does happen when you do your experiment, right? So take a coin, for example. Here's a lovely quarter. I flip this coin and I land on heads, and then I flip this coin again, and I land on tails, and then I flip it again, and I land on tails, and then I flip it again, and I land on tails. It might have happened to me with my finger. Flip it again, land on tails, and you're like, okay, so I have 5 times I've done this. And my experimental probability of heads, we look at that as probability of heads, by the way, when we're talking about, but this is experimental, is 1 out of 5. And then of tails, it's 4 out of 5. But really, if you're looking at theoretical probability as the number of ways an event can occur, so if you're looking at a coin, my options or my equally likely outcomes are either heads or tails. And that's it. And so if it's a fair die, you should be equally likely to land on one side or another. So the probability of heads should actually be 1/2, right? Because 1 out of every, like 1 way to land on heads, 2 outcomes possible. And then the same thing for tails. The probability to land on tails should be 1. There's 1 tail out of 2 sides. So if you look at this, like a theoretical probability of 1/2 is way off from the experimental probability. And that often happens. All right, so experimental probability, that was yesterday. This is today. All right. So theoretical probability, I just did this without really telling you what it was before. So P of whatever means the probability that the event will happen. So it dice P of 5, and I say up like the parentheses with the 5, and it reads P of 5, or probability of rolling a 5. Okay, so an experiment consists of rolling a dice. Find the theoretical probability of each outcome. Well, probability of 5. So you have to figure out, it's always a good idea to figure out the total number of different outcomes you could have. Well, in the dice, remember we did that sample space stuff, right? So 1, 2, 3, 4, 5, or 6. Those are my different outcomes. So I have 1, 2, 3, 4, 5, 6 of them. So my denominator is at least going to start off as 6. Now it might change because we have to reduce or what have you. But so probability of rolling a 5. Well, how many 5s do I have in here? I have 1. So it's 1 out of 6 possibilities. The probability of rolling an even number. What are my even numbers? 2, 4, 6. So I have 1, 2, 3 out of 6. And then that's I'm saying like your denominator will start at 6, but it might change because we would want to reduce 3 out of 6 to 1/2. For right now, I'm just keeping these as fractions, but remember, like we talked about yesterday, you can have them as decimals, you can have them as percentages, and you really just want to find figure out what the question is asking for, because it might be very specific if it wants you to answer in decimals or percentages or fractions. All right, P of 2, here's 1, 2 out of 6. P of 3, well, there's 1, 3 out of 6. So a lot of those are 1, 6. You can also have stuff like, probability of not a 4 or a 5, right? So if I don't want 4s and 5s, I have 1, 2, 3, 4 ways of doing that. So 4 over 6, which would be 2/3. So there's a bunch of different probabilities you can do that won't end up as 1 over 6. All right. Experiment contains a deck of cards. Find the theoretical probabilities of each outcome. Well, in order to do this, you have to know about cards, right? And we kind of talked a little bit about it at the end of the lecture yesterday. So first of all, there are 52 total cards. Okay. There's 4 suits. Suits meaning hearts, diamonds, spades, and clubs. Okay. So each of those has 2 through 10, Jack, Queen, King, Ace. So there's 13 cards in a suit. All right, so 4 suits, 13 cards per suit. And if you have played cards in your life, you probably know all this already, but I'm just helping everybody out. So if you're looking at the probability of an ace, well, I could have the ace of hearts, the ace of diamonds, the ace of spades, or the ace of clubs. So that's 4 different aces, and I have 52 cards total. So 4 out of 52 would reduce to 1 over 13. And then for 2, it's kind of the same thing. I could have the 2 of hearts, the 2 of diamonds, the 2 of spades, or the 2 of clubs. So that again is 4 out of 52, or 1 out of 13. All right, so probability of a face card. Like I said yesterday, a face card is Jack, Queen, King. So again, remember you have Jack of hearts, Jack of diamonds, Jack of spades, Jack of clubs. So you have 4 jacks, 4 queens, 4 kings. So I have 12 total face cards. So 12 over 52. And do me a favor real quick and don't reduce this yet. Because if you look here, this is probability of not a face card. Remember, we kind of talked about that yesterday. Like, I think it was a green on a spinner. You either land on green or you don't, right? So you're either a face card or you're not a face card. So if 12 of them out of 52 are face cards, take 52 minus 12 and you get 40. So you have 40 are not face cards. So you want to reduce, of course, now. So this would be 4 out of 13, right? And then this would end up being, hold on, 12 out of 52. It should be, oh geez, I can't work my calculator today. At all. Yeah, 3 out of 13. That was silly, because I'm like, I know the other one should be 10. What's going on? So 3 out of 13, this would be 10 out of 13. So you can reduce earlier and get the same thing if you want. I just wanted to show the actual totals of the cards, which is why I do not reduce quite yet. But this bottom part essentially says exactly that. So P of face card, P of not face card, what do the probabilities add up to? Well, 12 out of 52 plus 40 out of 52. Remember how you add fractions, right? So your denominators have to be the same, and they are. So that's cool. So this is going to be 52. And then I add the numerators. 12 plus 40 is 52 over to 52, which reduces to 1 or 100%, right? So your probabilities of things that are opposites and take up all of the outcomes possible is 100%. So again, like, why is this? Well, you're either a face card or not, right? There's no other option. You're either, a jack, queen, or a king, or you're an ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's fine. And then this next page kind of takes that and goes a little bit further with it. And I believe yesterday I referenced like the Scrabble letters and said, wouldn't that be a huge pain in the butt to like add all this up? Well, this is why, we take this concept of subtraction, right? So the probability, again, of an event happening or not happening is 1 or 100%, because the event either has to happen or not happen. Again, there's no other option. So those have to equal 100%, which is, again, why you can use subtraction in this rather than continuously adding the others. So a box contains only red, black, and white blocks. The probability of choosing a red block is 1/2. Probability of choosing a black block is 1/4. What's the probability of choosing a white block? All right, so I have 3 options. I have red, black, white. And I know adding those all together, the probabilities of all of those, should put like that, sorry, plus P of white has to equal 1 or 100, whatever. So probability of red is 1/2. Probability of black is 1/4. Probability of white for right now is X, and that all equals 1. So, I mean, you can look at this and hopefully you'll say, oh, okay, well, that's 3/4. But if not, you can change this. You can add it together. So 2 to 4, that becomes 2. So 2/4 plus 1/4 is 3/4 plus X equals 1. And then 1 minus 3/4 would give you 1/4. So probability of white is 1/4. You also, if you wanted to, could have changed those to decimals, but either way. And if you're like really not comfortable with fractions and you're like, how'd you get 1/4 from 1 minus 3/4? Remember that 1 equals 4/4. Anything over itself is 1. All right, number 2. A jar has green, blue, purple, and white marbles. Probability of green is 0.2. Probability of blue is 0.3. Probability of white is 0.1. What is the probability of purple? Right, so again, this will be probability of green plus probability of blue plus probability of purple. Oops, I don't know why I put a B for purple. Plus probability of white. Probability of green is 0.2. Probability of blue is 0.3. Purple, we don't know. And then plus white is 0.1. And that, remember, all has to add up to 1. So 0.2 plus 0.3 is 0.5 plus 0.1 is 0.6. So 0.6 plus X equals 1. 1 minus 0.6 will give me X equals 0.4. So the probability of purple is 0.4. All right. Distribution of letters in the Scrabble table is in the right, or Scrabble is in the table to the right. Find the probability of choosing a vowel and the probability of choosing not a vowel. Don't include blanks in either one. Okay, so I believe I just didn't put blanks in here. So the first thing you'll have to do is total all of these up. I actually want to say they total up to 98, but I don't remember because I feel like it was 100 and then the 2 blanks, but let's see if I can read this. It's really small. 9 plus 2 plus 2 plus 4 plus 12. Ooh, lots of E's. Plus 2 plus 2 plus 3. I did that in order. 12, 2. Okay, so I have that 2 and then that 3. Okay. Oops, not times. Jeez, repeat. 9, 1, 1, 4, 2. Could add some of these in my head. I just don't really feel like messing with it right now. 6 plus 4 plus 6 plus 4 again, plus 2 plus 2 plus 1 plus 2 plus 1. Bam. Okay, so, yep, there you go. I should have just trusted my instinct. So I have 98 total. All right, so we have to kind of decide together what we think are vowels. A-E-I-O-U, right? Of course, A-E-I-O-U. Then there's sometimes Y. So do we want to count it or not? No Y today. So A's and E's and I's and O's and U's. So A, there's 9. E, there's 12. I, there's 1. Oh, where's O? There it is. O, there's 8. U, there's 4. So if you add these together, let's see. We have 10, 22, 30, 34. So I have 34 over 98. And of course, you can see those are both even numbers. So we know that we can reduce that. So 34 over 98, and then math, enter. So I get 17 over 49. And then probability of not a vowel. Well, guess what? I don't have to add all the non-vowels together because you're either a vowel or you're not. Except if you're Y, but we decide not to count Y. So all we have to do is take 98 minus 34 or 49 minus 17. We're going to have to reduce anyways. Might as well take that one. We get 32 out of 49 for a not vowel. So again, that idea of subtracting can really save you quite a bit of time. All right. Here comes, like, this is my very favorite. And I will post this video too. I'm not going to actually give you the answer to it on this video. I'm going to just stop it there, and then you guys can like look at the video on my website and go all the way through. But such an interesting problem that I really, really love to do. Of course, it says with the people at your table. Well, sorry. With yourself, consider the Monty Hall problem. So I will end with that. But before I do, real quick, I just want to look at, so you have, this is your optional assignment today, is this 10-6 practice B, which you can also download from my website. So you're just looking at theoretical probability of each outcome. And it's pretty straightforward. So again, like rolling a number less than a 4 on a standard number cube. So 1, 2, or 3. And I have 6 possibilities. It's a 3 out of 6 or 1/2. Okay, so just make sure that you reduce fractions if that's how you're going to do it. Okay, or you can do a decimal or a percent. Now, I would, if it's given to you in some way, I would keep it that way. Like number 5 says the probability it will snow is 60%. What's the probability it will not snow? So since that's given in a percent, I would probably just keep it in a percent. That would be easier. All right, but now we're gonna go to the Monty Hall problem. And like I said, I'm gonna stop this before the answer comes up, and I want you to kind of try to figure out what you think. But I will also point out that one of the reasons this is my favorite video, like of all the year, is because the guy's voice is just fantastic. He's, I believe, from Australia, and he's like, hello. Sorry, I don't know why. I love it so much. All right, so without further ado, the Monty Hall problem. If I can get it to play, I might just have to do this in a second. Okay, here we go. Listen.
Hello. Welcome to the Monty Hall problem with me, Ron Clark.
Ron Clark.
Imagine you are on a game show. The game show host shows you 3 doors.
All right, that's obviously not where I'm going to stop it. I just want to turn the volume up a little bit because I'm not sure you can really hear it that well. All right.
Behind one of the doors is the star prize, a car. Behind the other 2 doors are booby prizes, 2 goats. You have no way of knowing which door conceals which items, and whichever door you pick, you'll receive the prize behind it. You are asked to pick a door. But before it is opened, the game show host opens one of the other 2 doors. Now the host knows where the car is, and he always opens a door to reveal a goat. You are then asked whether you'd like to swap your chosen door for the one remaining closed door. The question is, should you swap? Should you stick with your original choice? Or does it make no difference what you do? Which would give you the greatest chance of winning the car? I'll give you 10 seconds to think about it.
All right. So here is where I'm going to stop it. Because this is where, like, you'll have to, he'll give you the answer after this and he'll do the explanation behind it. So I want you to think about it. So again, like he said, you have 3 doors in the beginning. Your goal is the car. I mean, unless you want to go to which, whatever. But, and so you're like, well, I think door number 3. And then he knows that there's a goat behind door number 2. And so he opens that one. He's like, okay, well, here's another. So what should you do? Do you want to switch to door number 1 or do you want to stay with door number 2? So I need to try to kind of figure that out and like talk your way through it and see what you think you should do. And then watch the video and see if you were correct. So it's an interesting thing to think about. But that is it for today. Like I said, I'll post the Monty Hall problem as well, so you can start it, unless you want to hear him again, start at 124. But yeah, he'll give you the explanation for it. So it'll be neat. All right. I hope you guys have a great day. Talk soon.